In the last video, we saw that if you have an array variable like int a open close square bracket 10, remember this is allocated from the stack. And if you were to look at what a actually is, it's just a pointer to an int, just like if you said int star a. But there's one big difference. It's more than just a pointer variable. It's actually a const int star. What that means is it's the pointer or the position, the address that a in this case points to, it has to be a const. It can never be changed. So it's like saying it's a final value in Java. So the array was allocated in memory, and actually it's only allocated in the stack. The book doesn't talk that much about stack versus heap, but that's, you guys know what that, if you have a variable like this, that's where it's allocated from. It's allocated from the stack. And this variable a must always point there. It cannot be changed. If you try to change it, you'll just get an error message. So this is in contrast to ordinary pointers. So if you had an int star p, sure, you can change it any number of times. Whereas a, you cannot actually change the location that it points to ever. It's set when you create the variable in the stack. Dynamic arrays are used mainly to overcome some of the limitations of these static arrays. And as we saw, we have to specify the size, and this may not be known until the program runs, and so that can be a problem. Sometimes we have to we can get around this by estimating, for example, a maximum size. So we can, in this previous example, you can say int a, I think I'll need maybe 1,000 elements at the most, so you can allocate an array of size 1,000, and then if you end up using only some of it, then, well, a lot of the array is wasted. So sometimes you have to estimate the maximum size. It's okay, sometimes not. It can waste memory. The whole object of dynamic arrays is to have arrays that fit your problem. You can grow and shrink, and also, as you saw, you can set up data structures. That's what we'll do later on in this semester, is that we can set up complicated data structures where they are all linked together, or they have whole chunks of memory that are linked together, and if you allocate memory in one function, it'll stick around for other functions to use. Sometimes we need that. And at the same time, we also have to watch out for memory leaks. That is, you allocate memory in a function and it sticks around longer than you're supposed to stick around. Okay, so those things are advantages. Dynamic memories has a lot of advantages, but you also have to be very careful about how you use it. How do you create a dynamic array? Very simple, just use new. Okay, so here's a simple example. You see double star d, and then d is equal to new double square brackets 10. So you're allocating memory for 10 doubles. Remember, a double is 8 bytes, so this is 80 bytes of memory allocated from the heap. And we've seen this. We saw a number of videos ago. We set up a dynamic array, which is what you want to use if you're going to do anything with primitive data types and new. You never say d is equal to new double without open close square brackets, because what you would be doing there, if you didn't have this open close square brackets 10, you would be allocating a single double. Once again, something you probably never have to do. Very unlikely. To the point where I would say, if you see yourself doing that, it's probably a mistake. Okay. How do you delete a dynamic array? You use the delete, but here's the difference, is you have to use this open close square brackets. So this deallocates all the memory for this entire array d, which we had allocated earlier using new. So if you allocate 80 bytes, that is 10 8-byte doubles, you would delete it using delete open close square bracket and then the name of the variable. So this deallocates all the memory for this dynamic array. The brackets indicate that there's an array, it's not just a single location. So d, after this delete is done, d still points to that memory location, and so to make it so that you don't accidentally use that memory location, which is now maybe used by some other part of your program, you should set D to null. So that's always a good practice to set your deleted variables equal to null as soon as possible. You can have functions that return an array, but one thing you have to watch out for is it doesn't work exactly like in Java. So in Java you might be able to do this. You can say int open close square brackets some function. So this could be a method in a class. This would be legal in Java. C++, not. You cannot do this. This is illegal. You have to use pointer notation. So you have to say that this function, even though it might be returning you an array rather than a pointer to a single int, you have to return a pointer to an array base type. So that's one of the things that are sort of unfortunate about C++ syntax. Personally, I think this syntax would have been better, but C++ uses this. You can do pointer arithmetic, and I think we saw this a few times, a few videos ago. Let me just take a quick example. One thing I'll point out, and we actually did look at this a few videos ago. Let's say D is of type double pointer, and double pointer is just an alias for pointer to double. So D is just a pointer to double, and let's say now you allocate 10 doubles, which is 80 bytes. Remember that a double is 8 bytes. So if you say D, that's just like saying D open close square bracket 0, that is the first location. D plus 1 will not refer to the next byte, but will refer to the next double in this array, which is essentially just D open close square brackets 1. So you can think of this open close square bracket 1 as doing some array arithmetic or pointer arithmetic, and that's actually what it does. And this plus operator is actually overloaded to for each type. So if D is a double pointer, the plus 1 means you add 8 locations, because each double is 8 bytes, at least on our system that we're using. Most of the systems we use today, a double is 8 bytes, and so when you add 1 to this D pointer, you're adding 8 to the memory address. And if you want to take a look at that, let's just set up a quick example. I'm going to get rid of some of this other stuff. I don't need much of this. I'm going to say double star D is equal to new double 10, and then we can print out P, and then what we can do is P++, and you can do that in C++. You can't do something like this in Java. And let's print out P again. So remember that this will print out something in hexadecimal notation. So if you've never seen this, it's kind of hard to read if you have something that ends in a letter like A, B, C, D, or F, which is allowed for hexadecimal values. Luckily we're, oh good. So here, notice, we lucked out. The first location of this array, that's P sub 0, ends in a C0. You bump up P by 1, and you see that it goes up by 8. We lucked out. We got good values. But if you were to try this, you might see, if you start out at location 2, if this were a 2 at the very end, and you bump it up by 8, it would go to 10, right? Well, 10 is represented as an A in hexadecimal. So if this started out at 2, you would see an A. Started out at 4, this would end up being bumped up to C. Okay, So if you get values like that, don't get confused. It's because these are hexadecimal. The X means hexadecimal. Okay, so that's pointer arithmetic. We have looked at it in the past with integers. Now this is just another example of doubles. Doubles are 8 bytes. You want to keep that in mind. So you can use this pointer arithmetic in your code. That said, it's probably another thing that you should never have to use. So you can actually do this. You can say, I want to bump up D by 1. So that's not an L. It looks like an L, but it's just so that you can only bump it up by int values, I believe. And so if L were an int value, yeah, I guess you could do it. So let's say you bump up D by 1. That's just a pointer, and then you can dereference this whole thing. That's what you're doing with the star and parentheses. You're saying bump up D by 1. This is exactly the same as saying D open close square bracket 1. Okay, so it's completely equivalent to doing that. Now, why would you ever want to use this? There is no good reason to ever want to use this. You can just as well use this. You can only do addition, subtraction on pointers. You cannot do multiplication or division. That is, you cannot do multiplication division like to D. You can't say D divided by 2. You can do D plus 1 or 5 divided by 3 or whatever. You can do that, but you cannot do a direct operation on a pointer that involves multiplication or division. Some low-level code, yes, will do stuff like this. They will even do bit shift operations, and those are particularly hard to figure out what they're doing, but those are legal. Then there are some systems programming, that is when you write device drivers and things like that. Yeah, those kinds of operations do come in handy. We can use pre or post increment or pre or post decrement on pointers too. Can you do multidimensional dynamic arrays? Yes, of course, these are extremely handy. And in Java, all your dynamic arrays, all your multidimensional arrays are dynamic. So these are just arrays of arrays. So you can have, for example, create a two-dimensional array, and you might, as you might guess, that is, so int array pointer is same as int star. And now when you say int array pointer star, that's like saying int star star, and actually that is completely legal. You can say int star star. You can have any number of levels of pointers to pointers to pointers. It can get pretty confusing, and so as much as possible it's good to use what Java uses, but remember also that there are some limitations to doing that in C++. So now you can allocate, you can think of this as M is a pointer to pointers, and so this, you can think of these as the rows if you want, if that helps. You don't have to, but you can think of these as rows. So now you're saying you have 3 rows, or you can think of this as saying you have an array of 3 pointers. And for each row, you can have 4 columns. You can think of like that. That would, if that helps. And that's usually how we think about these. We say for each row, m sub I, for the ith row, create a row that contains 4 columns of data. And this creates a 3 by 4, that is a row by column. 3 rows by 4 column dynamic array. Okay, in the next section we'll go back to classes.